Okay, welcome back. So for the remainder of the morning before lunch, we're going to talk about recent results from two different types of measurement. In the case of the first talk, this will be given by Paul Lucey on laser reflectivity results. I think he's going to talk about both Mercury and the moon. Obviously, we've seen that these two different bodies have a lot to teach us in terms of their similarities and their differences. And I know Paul is going to present some really exciting recent results that correlate the laser reflectivity with some of the thermal measurements that Dave Paige has talked about. Paul.
Okay, thanks everybody. You saw some of the great results from the Mercury laser altimeter that Dave showed, and today I'm going to talk about similar data sets derived from the Lunar Orbiter laser altimeter on LRO. This is a schematic here of the Lolo instrument right here. It has a laser transmitter, and then here's its laser receiver. And Lolo, of course, is primarily designed as a cartographic instrument, measures the range to the surface extremely precisely, and knowing the orbit of the LRO spacecraft, the topography of the moon has been measured with extreme precision. But as Dave mentioned for the MLA instrument, the Lolo instrument also measures reflectance, and let's see, just show where Lolo is here on the LRO spacecraft. So Lolo is right here, and you can see its little transmitter receiver corresponding over here. This measurement is actually, I find it actually fairly remarkable. Here's the Lolo transmitter is about 60 milliwatts. It's at the high end of a consumer level laser transmitter. And here's an example, recent example of that being used in the field. This is a helicopter in Tahrir Square apparently being levitated by laser pointers. These are, so the kind of transmitter on Lola is a fairly low power transmitter. And you can think of the laser beam that comes out of, the laser pulse that comes out of the transmitter is only emitted for a few nanoseconds, and you can think of it as a cylinder about an inch in diameter and about 10 feet long. With the divergence of the Lolo transmitter, by the time it gets to the surface, the laser pulse is approximately a sphere about 10 feet in diameter. That impinges on the lunar surface. Now, lunar surface is irregular, so it reflects the light in all directions. And that laser pulse you can think of as an expanding shell that comes out from the transmit point. By the time it gets up to the Lolo spacecraft, that shell is 50 kilometers in diameter, about 20 feet thick, and the Lolo transmitter picks about a 6-inch piece of this 50-kilometer shell to produce its signal. In terms of how much signal we're actually retrieving, if you think of the national debt as $16 trillion, so if Lola puts out 16 trillion photons, after this whole process, for that 16 trillion photons put out, Lola gets 1 photon back from the lunar surface. So that's obviously a government project. Now, Lola actually puts out a lot more photons than that, but the net result is for every Lola pulse, we get about 600 photons back from the lunar surface. Of course, the actual number we get, it depends on the lunar reflectivity, which is the topic of what we're going to talk about today. In fact, Lola is so sensitive that we want to avoid these guys here. These are the lunar retroreflectors left by Apollo astronauts. It's 11 on the right and 15 on the 11 on the left and 15 on the right. These would return so much laser signal to Lola that it would damage the Lola receiver. Of course, combined with Lola and NAC, we know where these things are so accurately now that Lola can get very close to these. But up to very recently, there was an exclusion zone where Lola was not taking data over the Apollo sites. Okay, the quantity that Lola actually measures is called normal albedo. This is when the angle between the transmitter, the surface element, and the receiver is 0. And so for a dark surface like the moon, the normal albedo is independent of the incident and emission angle of the surface element. So it removes the effect of topography from the lunar surface, or from Mercury's surface as well. Now, you can measure at this normal albedo condition, also known to astronomers at zero phase, from space using the sun as a light source. And here's some examples. The view from the Earth, this is at full moon. Galileo viewed the moon at this position, getting a near full moon or a near zero phase observation over Orientali Basin. Apollo 17, also a near zero phase observation. But in all these cases, nadir views are confined to the equator. If you want to get zero phase observations using the sun as a light source in the polar regions, you have to have extremely oblique lighting. Okay, that said, this is summing a year's worth of Lola observations at 1064 nanometers. These are equatorial projections showing that the Lola zero phase observations are dramatically capturing the albedo variations on the moon. But these are the kind of views that we see very commonly. These are entirely new. Besides me and Dave and the people on the Lola team, these views have not been seen by anyone else previously. This is the lunar North Pole, the lunar South Pole observed with no topography corrupting the measurements of the albedo. Just to bring that home, here's a whack mosaic taken at almost the same projection. Here's this. Let's see. Here's the South Polar region, and you can see that the imagery is dominated by topography. Here's that same region from the Lola data with showing no topographic influence on the reflectance measurements. So that means we can quantitatively compare any portion of the lunar surface and also to Mercury in a very unique way that doesn't involve photometric corrections and various assumptions. I'll just show one slide about Mercury. Here's comparing the reflectances of Mercury and the moon. These are both from these laser altimeters. So Mercury is almost 3 times darker on average than the lunar highlands. The red curve is Mercury. The black curve is the whole moon, equal area projected. And then the blue curve is just the polar region. So the Mercury is considerably darker than the moon. Mercury is about the same reflectance as the lunar Maria, or the average Mercury. And this little bump down here, this is for the polar regions, is the famous Mercury dark deposits, the MLA dark deposits. There are no exposures, I'll just preview that, there are no exposures on the moon similar to the MLA dark deposits. Okay, the first paper that used the Lola reflectance measurement was Maria Zuber et al. Last year, where they did a study of Shackleton crater, multi-dimensional study, but the reflectance description focused on the fact that here's Shackleton. It's shining like a little beacon here very near the South Pole. And they noted, obviously, its anomalous brightness compared to the surroundings, and offered basically all of the hypotheses for what could cause this reflectance anomaly. And so we're going to go through the Shackleton example, and then using the Lola data for the whole polar region, show where we're at as far as understanding the polar reflectance. So just to talk about Shackleton real briefly, we've now compared the reflectance of Shackleton to similar sized craters moon-wide, and Shackleton is anomalous, but is not an extreme value. So here's the reflectance of the interior of Shackleton, and here's the normal albedo of similarly sized craters in the equatorial region. You can see that Shackleton is bright, But there's been a recent development in that these craters, Shackleton has been shown to expose the northocite in its upper rim based on the illuminated portion of the rim from data from the Kaguya satellite. And these craters down here in the, at the highest normal albedo are equatorial craters that also expose the northocite. So Shackleton isn't a terrific example of studying whether or not there's an excursion in reflectance in the polar regions. So what we've done with the Lolo data for both the north and south pole is compare the reflectance in regions of permanent shadow to the regions outside of permanent shadow in a whole bunch of different ways. So this is an example of a map of permanent shadow. This is an illumination map generated by Andy McGovern. A paper, I guess, is coming out now at Johns Hopkins. And so this is a subset of those data. He produced a map of percent illumination over long epochs, and this is the percent being 0. So these are areas that are permanently shadowed. In Dave's material, those areas all have very low reflectances. Okay, so cutting to the chase here. Here are histograms of the normal albedo of areas, in this case, in the North Pole, which are sometimes illuminated in the blue and versus in permanent shadow in the red, normalized to their abundances. The permanent shadow from the previous map obviously is much less extensive than the rest of the polar regions. And so it's clear that there is a persistent offset, a consistent offset between the reflectance in the permanent shadow and sometimes illuminated. Okay, so I'm done, thanks. Oh, I guess there are a few more things to say. Okay. All right, so the permanent shadow is different, though I should obviously point out that there are regions that are sometimes illuminated that are as bright as portions of permanent shadow and vice versa. The distributions aren't separated, but the distribution as a whole have split. So I'm going to talk a few minutes about some alternatives to volatiles as an explanation for this permanent shadow and some tests we've done using various data sets. So the principal alternative here is space weathering, a difference in space weathering properties in the permanent shadowed regions. Space weathering was first recognized way back in 1955 by Tommy Gold at Cornell. He noted that craters, that rayed craters, there were morphologically crisp craters on the moon. Some of them have rays, some of them don't. The ones that have rays always superpose the ones that don't have rays. So he inferred that there's some process is altering the uppermost lunar surface on short timescales. Well, now after returning Apollo samples, we have a process we call space weathering. It principally is alteration of the chemical, physical, optical properties of the moon from micrometeorite bombardment and solar wind sputtering. There's controversies about the relative importance of those two processes. But basically, both of those two processes produce vapor-deposited rims on pre-existing mineral grains that are full of tiny little iron spherules. And these are nanometer scales. They range in size from some 1 to several tens of nanometers. In this size range, which is way below the wavelength, an absorbing particle is an extremely efficient absorber, and its efficiency is a strong function of wavelength. The result of that is that this material where these rims accumulate is considerably darker than typical lunar material. So here's a plot that shows the spectrum of some Apollo 11 rock samples. These are pulverized, measured in the lab. The Lolo wavelength is shown there in the green. So a pulverized rock to Lola would have this high reflectance, but the Apollo 11 soil samples, which have been exposed to this space weathering process, would have this factor of 2 lower reflectance. Okay, so one of the hypotheses raised by Zuber et al. Is that mass wasting could have increased the reflectance of Shackleton crater. So let's look at a little example here. This is a little crater about the same size as Shackleton. Looks like a little Cheerio. It has steep walls. It's shedding material down its walls that are not weathered. And so this other unweathered material is bright. It has not accumulated these vapor deposited rims. You can see all through this image there's little rings in here. These are all caused by mass wasting, downslope movement of debris, exposing fresh surfaces. So we can compare that to a slope map derived from Lolo. So, and I'm going to flip back and forth here a little bit. And you can see many of these surfaces, many of these ring-shaped surfaces correspond to steep surfaces. There are a few other features. For example, this one up here. This is a little fresh crater. It's so small it doesn't even appear in this map, but it makes a big immature exposure. But the point is that mass wasting or steep slopes can cause in this landslide of Apollo 17, just an illustration, this mass wasting can cause the surface to become brighter. So what we did was a simple experiment. We used that slope map to compare the reflectance in and out, just to show in the same kind of plot we've been showing here. This is the equator again in this case. So this is the all slopes and also slopes less than 10 degrees. And then this nearly invisible green line here is the distribution of reflectance of steep slopes. Those are larger than 20 degrees. So we're going to use the same. So this shows that mass wasting does increase the reflectance, so we need to control for mass wasting. So in the polar regions, what we've done is take the Lolo slope data and constrain the data so that we're only looking at shallow slopes. Less than 10 degrees, mass wasting cannot operate. And you can see that controlling for mass wasting, we still see a consistent increase in reflectance in the polar regions in permanent shadow. This difference even persists to when we constrain to steep slopes alone. So here's the case where greater than 20 degree slopes in permanent shadow are also brighter than steep slopes out of permanent shadow. So something very consistent is going on. We consistently see an increased reflectivity in permanent shadow that's independent of mass wasting. Now, there's another issue about space weathering that Zuber et al. brought up, which is that these regions in permanent shadow tend to be in the bowls of craters. They do exclude some of the sky, so they hypothesize that the micrometeorite and solar wind flux can be lower because they're excluding some of the sky in the bottom of these craters and near steep slopes. So they produced, through ray tracing, a sky access map. I'm reading it over here. So the sky access is computed from the Lolo topography. And now we can control for that effect too. So we'll look at two cases here. Here's this effect of large sky views. These are basically regions in and out of permanent shadow that are distant enough from walls that they have negligible shielding from solar wind and micrometeorites. And this is our familiar offset. But when we do control for the sky access, we see that there's still a consistent offset. These are regions where there is significant shadowing of the sky from the solar wind and micrometeorites, and we still see an offset between the two populations in and out. So if we can take the sky axis as a proxy for the intensity of space weathering, as opposed to this mass wasting process, and we still see a persistent difference between permanent shadow and not permanent and impermanent shadow, I guess. Okay, now the last parameter that we looked at, which is kind of an analogy for temperature, and then Dave is going to say a few more words about this, is we looked at the difference in reflectivity on pole-facing and equator-facing slopes, constraining those slopes within plus and minus 45 degrees of the pole-facing direction or opposite. And so you can see that that the equator-facing slopes are similar to all slopes, whereas the pole-facing steep slopes, in this case, this is constraining it to just steep slopes, are significantly brighter. Now, the pole-facing slopes are the ones that Dave explained tend to be brighter. Now, there seems to be some violence done to my slide. Oh, it did work here. So, just concluding about the reflectivity, the permanent shadow is generally more reflective than the areas that are sometimes illuminated. Space weathering, both in terms of slope as a proxy for mass wasting or sky axis, which is a proxy for intensity, do not account for the differences between regions in and out of permanent shadow. Steep pole-facing slopes are more reflective than equator-facing slopes, and we're left with basically two hypotheses. The surfaces in permanent shadow are somehow less susceptible to space weathering, meaning that at the same intensity, they react less, or we have volatiles there. And then I'm going to turn it over to Dave for a sec to see the temperature correlations.
The data set that Paul and the Lola team have come up with is very interesting and exciting, although, as Paul has demonstrated, it's not entirely straightforward in terms of its interpretation. And let me pop this up here. What we're looking at here is let's go back to the North Pole. On the left is the diviner annual maximum measured channel 8 brightness temperatures, which is a pretty good indication of how hot it gets at the surface. And then on the right is the Lola reflectance data set, the same one that Paul showed in map form. Now, you can see here by looking at it that these two don't really look all that much the same. There are interesting similarities in that a lot of these craters do appear to be bright, but there's also some sort of larger scale trends in the data set which are due to things like crater rays, geology, who knows what. And so the idea is to try to disentangle between these two data sets to see if we can maybe find a real temperature signal between the two. This is the same situation in the south here. I'll point out Shackleton crater, which is this bright crater right here, which is an obvious cold polar trap. So, we're done, right? Well, so the first thing we tried to do was just the same thing we did in Mercury, which simply cross-plot the two data sets relative to each other. And I'll show you what those plots look like. Here is, it's a little bit cut off on the bottom, but this is annual maximum temperature, 100, 150, 200, 250 Kelvin, and then Lola albedo. This is the North Polar region plot. You can see that there is a discernible general trend of increasing reflectance with decreasing temperature, which is the same one that has shown up in the analyses that Paul has done. And here's the same result in the South Polar region. Again, similar. There are some interesting little things going on here, but the question is, what's really going on? And the goal of our analysis is to try to figure out a way to beat down this, what I'll call geologic noise that appears to be on the reflectivity signal here. And an approach to doing this is to simply confining the analysis to relatively symmetrical shaped impact craters. And so the idea here is if you have an impact crater, to first order, the composition is probably, as long as it's small enough, is probably all similar, and that as you go around the crater azimuthally, all the geology is more or less the same. And so what we did was, and this is very recent work, is we basically outlined the boundaries of all the impact craters in both polar regions. This is something like a total of 400 impact craters. And then confined our analysis to just look at what's going on inside the craters, but not in an absolute sense, but in a differential sense. In other words, and I'll just show you an example. Here's a crater we call NP 181. And this is the one of these we got really excited about, right? Because you can see here that it's got a big cold trap in this quadrant here. This is the brightness temperature map. And this is the Lola reflectance map. And you look at this, whoa, there's the ice, yay, okay. But the question is this brightness that we see in this area here unusually bright relative to the general trend that we're seeing, okay? So the procedure was as follows. We took all of the data inside each crater, and then we normalized everything to what the measured reflectance was when the temperature was about 255 Kelvin, because we could almost always find that temperature in every crater that we looked at least some part of it had that. And then we normalized that to have a reflectance of 1, and then we saw how the rest of the crater deviated from that reflectance as a function of temperature. And the compilation of all these results are shown right here. So at roughly 255 Kelvin, and I'm struggling to find my cursor right here, by definition, all the reflectivities are 1. And then in all the rest of the craters, the red ones here are the north polar, and the blue ones here are the south polar ones. What we see come out of this is a very, very consistent monotonic increase in albedo with temperature, starting way down at 350 Kelvin and going all the way down to roughly 100 Kelvin. And it's the same in both poles, and it's very consistent. And so we've got to, given that I think volatiles are out of the question up here at 300 Kelvin, we got to believe that this is the space weathering component, or at least some sort of textural, temperature-dependent space weathering component in the data set. But the interesting thing is what happens here at the lowest temperatures, at least in the southern data, we get a pretty strong deviation from that. And this could be due to low sampling, the fact that those craters themselves, there's a limited number of them. There could be, unusual things going on in those craters, et cetera. But they provide some excitement for both of the hypotheses that Paul presented. One is there is some very nice regularity of temperature as well as some anomalies. And that's kind of where at least it stands as of this weekend. But who knows? There might be a lot of other things that may come out of our future analysis. But this idea of just looking inside craters and the differences it looks like a pretty good technique, at least to help sort out the geology from the thermal effects. Oded.
So this is very interesting. The first I've seen it. So, so if I got your bottom line here correctly, you're saying that the overall trend that you see out to warmer temperatures is not too valid.
I personally don't think that's the case, just because it's hard to imagine that at these very high temperatures you're mixing in anything that has a hope of being volatile related. Right, okay. And also, if it was volatiles, what we saw in Mercury, you'd see discontinuous jumps. There'd be something that happens at a particular temperature, and it's not showing that.
Slope remaining consistent all the way down to maybe 100 Kelvin leads me to believe that there's no reason to invoke another process until you get to below 100 Kelvin. Are you with me?
Yeah. South is the increased one. The North Pole is pretty boring, yes.
Yeah, okay. So in the north you see no such things in the south.
Right, but there's issues. We didn't pick some of the coldest craters in the north because they're irregularly shaped, and we thought they might have too much of a geologic impact. Maybe if we included, different boundaries or stuff, we might get different results. So that's kind of where things are at.
Dave, this is averaging all of those craters. Were there some that showed a strong signal and others that didn't, that maybe
Yes, we could imagine sorting it by crater diameter and doing all kinds of other statistics on this. Yeah. Oh yeah, I can show you individual craters that show beautiful variations, but some do and some don't. Yeah, we have a clickable map. If you want to play with this later, you click on you click on the map. You can see how it looks for your favorite crater. Yeah, there are some that show interesting stuff and some that don't. This is just the average. This is a way of summarizing the results.
And Dave, to what extent is the maximum temperature a function of albedo rather than the other way around?
Hardly at all. It's almost impossible to change the maximum temperature of something on the moon.
Yeah, that's very interesting. It's tempting to cherry pick more and more.
Yes, that's why I didn't do that for this meeting.
There must be a pony in the pile here someplace.
Yeah, we could easily show you a crater that, like that one we showed here. I mean, that looks just great there, right? But you know, if the thing about volatiles is you expect there to be regularity if it's caused by some of the phenomena we were talking about earlier.
Well, it's hard to explain away those that really do dramatically show it because you don't understand some of the other complexities.
That is as well. That's true. That's true. But I mean, this is an objective look at where we are right now.
And Dave, this is just considering the surface top 100 microns.
Absolutely, absolutely, right. And you know, are we looking at the tip of the iceberg or a little dusting of volatiles? Again, that's.
If you look then at the hydrogen data from the neutron spectrometers, it would say cherry picking is required because none of the moon looks anything like the other part of the moon.
Exactly, and this will be I think a consistent trend throughout the meeting here. Yes, that's why we need to have this this study. Yes.